Since the 1950s, air traffic in the United States has relied on radar technology to keep air traffic moving safely throughout the national airspace. For more than half a century, this system has worked well, but it was never designed to support the levels of air traffic we see today. As a result, flights don't always take the most efficient routes between airports, and a thunderstorm at a single major airport can have a ripple effect throughout the entire national airspace system, causing flight delays from coast to coast. To address the needs of modern aviation, the FAA, working in collaboration with NASA, other local, state, and federal agencies, and the aviation industry, has embarked on NextGen, the most wide-ranging modernization of the air traffic control system in the history of flight.
NextGen is the overhaul of FAA's old traffic management system. And the intent is to augment the decision capabilities of controllers by providing them more automated decision support tools and more capability to predict how the aircraft should fly. The current traffic system is predominantly radar-based. Radar has inherent inaccuracies. NextGen is going to be based on GPS, which provides substantially more accurate positioning of the aircraft. And also the communication, which is purely voice-based currently, is going to be more automated via computer-to-computer communication. NASA is contributing to the re-engineering of the airspace through developing concepts for optimizing the flow of traffic in various areas of national airspace or control entities.
Researchers at the University-affiliated Research Center are working in close collaboration with their counterparts at NASA's Ames Research Center to explore a wide range of new approaches to improving operations across the national airspace system. In the arena of surface operations, UARC and NASA researchers are looking at numerous approaches to routing and scheduling taxiing aircraft in order to reduce fuel consumption and shorten taxi time.
When we say surface operations, we mean the operations that happen at an airport. The aircraft pushing back from the gate, moving on the taxiways, taking off, then arrival aircraft landing on the runways, taxiing into the gate. Challenges on the surface operations, they kind of differ based on which airport you're looking at. But one underlying vein in all the airports here is you see a lot of delays either on the taxiways or on the runway.
Now, delay basically is incurred when an aircraft stops due to certain constraints, and the main idea of SARTA is to push back those delays to an area where the aircraft can be stopped and the engine can be turned off.
SARTA stands for Spot and Runway Departure Advisor. It's a system we developed here at NASA Ames, which is our tool for reducing congestion on the surface. It's a unified tool for advisories for the airline operators and air traffic control tower controllers.
One of our schedules is called the Spot Release Planner, which computes the optimal time for an airplane to be released from the spot in order to get onto the taxiway and go down to the departure runway. The other component of SARTA is a runway scheduler. And so our runway scheduler will look at all the departures wanting to leave and all the arrivals wanting to cross the departure runway and compute the optimal sequence for all these aircraft to be departing from the departure runway or crossing the departure runway.
So the expected benefits of SARTA are reduction in delays on the airport surface, reduction in fuel consumption on the airport surface, and reduction in emissions due to airport surface operations.
In addition to making surface operations more efficient, UARC researchers are also looking at ways to improve terminal area operations, increasing efficiency and throughput for airport arrivals and departures.
There are often a radar facility associated with the airport, a busy airport. So in the US, we call it Terminal Radar Approach Control, TRACON. And this facility generally helps guide aircraft from the en route area down to the airport or coordinate flight between the terminal areas. You can imagine Northern California TRACON area. So that include San Francisco, San Jose, Oakland, Reno International Airport, Sacramento International Airport, as well as other 19 smaller airports that it controls to. So when aircraft leaves its en route airspace, come down to land, there are going to be a lot of congestion. And that's the problem. Currently, we don't have much of an automation technology to help the controller. And in a busy area or in a busy time period, you can have extremely high workload from many of the controllers.
To address the issues of congestion in the terminal airspace, NASA has been working on a suite of tools called Interval Management, Terminal Area Precision Scheduling and Spacing, or IMTAPS. These tools, which include both cockpit and air traffic control technologies, are part of the joint NASA FAA project Air Traffic Management Technology Demonstration 1, or ATD-1.
So ATD-1 is a field test that is being done that's going to integrate next-gen technologies in the terminal airspace, and it's a way of actually having a real-world deployment and seeing how effective it is with real flights. So what ATD-1 is doing is it's implementing a scheduler that will assign a route that extends from the cruise altitude to the runway. Instead of the controller having to manage the flight through that entire phase, his job will be looking at the route, identifying whether the route is acceptable and accepting it, and then the aircraft would fly that route and he could focus on the next flight. So it's reducing controller workload, it's improving the fuel efficiency of the aircraft's descent profile, and it is also reducing delay.
In addition to surface and terminal area operations, UARC and NASA researchers are also looking at ways to improve en route air traffic management, making flight paths more efficient between departure and arrival airports.
The biggest cause of delay in the national airspace is weather, convective weather. What dynamic weather route, acronym DWR, allows us to do is that identify the most fuel saving, meaning the shortest path, through a weather scenario. The way dynamic weather route works is that we have data about all the aircraft in the national airspace. So we know their flight plan, we have their current position, and we have environmental effects such as wind and whatnot. Based on the model of the aircraft and wind pattern, and also the current position of the aircraft and their planned route, we can generate what's called the trajectory. Having the trajectory and having the model that predicts the movement and the intensity of convective weather cells, we can easily detect whether an aircraft is going to conflict with a given weather cell. And based on certain criteria, we can propose a deviation route for that particular aircraft. Benefit of DWR for the controllers is that it facilitates decision making, identifying the most efficient route around the weather. The benefit to the airline operators is that it allows for better managing the economics of flight. And also, if you're able to somewhat distribute the routes around the weather into multiple routes rather than one route, you reduce the congestion.
NASA is deeply engaged with the FAA in developing next-gen technologies to modernize our national airspace, and UARC researchers are playing a central role in support of this mission. Over the next 2 decades, many of these technologies will be incorporated into the U.S. air traffic management system, improving overall system efficiency while ensuring the U.S. national airspace remains the safest in the world.